So we're now going to do, so let's now look at a more complicated epsilon delta example. So we're going to look at the function f of x equals 2 x to the third minus 2x squared minus 5x plus 8. And then we ask, use epsilon delta to show f continuous at x equals to 1. First of all, what does this mean? So by definition, f continuous at x equals to 1 if and only if the limit as x goes to 1, f of x is equal to f of 1. So this is the thing we're asked to prove by using this epsilon delta definition. And first of all, what is f of 1? Well, f of 1 is equal to 1 minus 2 minus 5 plus 8 is equal to 2. So according to the epsilon delta definition, what do we need to do? So need to show, it can be good to write this down even if it's a bit of a mouthful. For every epsilon, there exists a delta such that for all x, then x minus 1 smaller than epsilon, and of course we have to take away x equals to 1. We could also subtract it from the set here, implies f of x minus 2 is less than epsilon. And here we may as well just write out the expression immediately. So how do we start such arguments? Well, let epsilon be arbitrary, fixed, unknown, and we want to get this thing here less than epsilon, or figure out when that happens. And we want to figure out when that happens in terms of this guy here. Oops, and here I did a misprint. This should of course be a delta. Then what? Well, the point is to start playing with this expression here. So we compute, and again, keep in mind, we want to at least leave the possibility open that we need to use some kind of chain of equalities and inequalities here. So let's not put in the epsilon immediately. So f of x minus 2, which I kind of reminded myself here is this thing. What is it equal to? Well, I mean, this looks sort of bad, but let's try to stay positive. So we get 6 here. Now, notice this is a polynomial, right? And also, if we are to have any hope that this becomes small when I insert 1 here, this polynomial actually has to have a 0 when I insert 1. And we can check. So 1 minus 2 minus 5, that's minus 6, plus 6 is 0. Aha, so this polynomial has a 0 at 1. But by the fundamental theorem of algebra, this means I can factorize this as x minus 1, and then some second degree polynomial. And since there's a 1 in front of the x to the 3, there will be a 1 in front of this thing. And then here I'll get a px plus q like this. So I know there exists such a factorization. How do I get this expression? Well, I can either play around a bit or I can use polynomial division. Playing around a bit will be my favorite thing. So the only way to get the 6 here is if minus 1 times q is equal to 6. So that means that the q must be equal to minus 6. So there's nothing else that would give us this constant term. Everything else when we multiply out will give us an x. So it will add to give some of this. And then if this works, what should p be? Well, what terms will give me this? Well, that's the minus 1 times this. So minus px, and then the x times this. So minus 6x. So this has to be equal to minus 5x for this identity to hold. And then moving things around, we see we can kill the x on all sides. We can solve for the p. So like this, I move 5 to the other side. So 5 minus 6 should be p. So this is minus 1. So here I should get a minus 1. Now, if you didn't quite follow this, what you should do now is multiply out this to see if you get this, which should work. Or if you want to do a bit more job, you can take this and divide by x minus 1 and observe that you get exactly this. Now, what's next? Notice here, hallelujah, this has appeared. And this is the guy that we're supposed to make small. And of course, now this expression here is morally proportional to this guy, so making this guy small should make all of this small. What can of course mess this up is if this expression gets close to infinity when x gets close to 1. But as x gets close to 1, this thing here is more or less 1 minus x, it's more or less minus 6. So it won't. And then you can ask, how big does it get? Well, that's more or less up to us. Because just as in these proofs for sequences, I can hear myself say that, well, I never make delta bigger than 1. So that we can do. So let's say, so we demand that delta is going to be a number smaller than 1. Here I can do smaller than or equal to or strictly smaller. Let's do strictly, since there are just strict inequalities here. So we are the ones choosing delta. So we now make sure that whatever delta is, we'll never choose it bigger than 1. This means what? This means that x to the square minus x minus 6. Now I can do this either using fine surgery or a hammer, okay? So I could, if I wanted to, figure out exactly how large this thing here becomes when this inequality holds with delta strictly smaller than 1, or I can just hammer my way through it. So let's do a little bit of preamble first. So this means that x minus 1 is strictly less than 1. If I open up the inequalities here, this means that x minus 1 is between this. And this means if I add 1 now, this means that my x is between 0 and 2. Of course, so if I have here 1, and I allow myself to go at most a distance 1 here and a distance 1 here, I'm going to be between 0 and 2. So when I make this demand, I'm really making this demand. So if you don't like inequalities, you can say that x is now in the interval between 0 and 2. And the point here would be to see how large can this be when x is between 0 and 2. And as I said, you either do fine surgery and maximize this expression on that interval and take the absolute value of that max or minimum. So I mean, if this goes down to minus 10 and up to 1, then it's the absolute value of minus 10. That's the largest that this can become. Or I don't do fine surgery. I just do a triangle inequality. So triangle inequality says what? It says that the absolute value of a plus b is less than a plus b like this. And here I can call this my a and, well, minus 6 my b. So this is then smaller than this. And now the minus gets killed here, so that's just a 6. And then I now have my x squared minus x, but this I can write like this if I want. Then I apply the triangle inequality once more. I get x to the squared plus minus x plus 6, but the minus gets killed here as well. And the absolute value of x times x is the same as the absolute value of x times the absolute value of x. So I'm getting this. And now x is in 0, 2, so all the x's are positive. So here I'm having x squared plus x plus 6, where all of these are less than 2. So this is less than 4 plus 2 plus 6 is equal to 12. So here should perhaps be more explicit. But what I did here was check that when x is between 0 and 2, this implies that this expression is less than 12. So all of this, you can say, is some type of parenthesis, right? Because what I'm really doing is I'm computing this expression here. So now what I know is that if I have the condition that x is in 0 to 2, this thing here is less than x minus 1 times 12. Oh my goodness. And what's the next thing? So let me move this parenthesis a little bit down. So what does this mean? Well, now I can put this thing here and ask, when is this less than epsilon? And this I can solve. You see that, well, this happens when x minus 1 is less than epsilon divided by 12. Aha. And this is basically what I want to choose for my delta. But of course, not quite. Because what happened? So here I put this condition, but let's write out this condition in terms of the delta. So this thing here was when x minus 1 was strictly less than 1. Then I can do this move, and then I can do this move if this holds. What does this mean? Well, it means that this thing here is less than epsilon if this is true and if this is true. Aha. So we conclude that if x minus 1 is less than 1 and x minus 1 is less than epsilon divided by 12, both of these, this means that f of x minus 2 is less than epsilon, whatever epsilon is, okay? But this means I've chosen two deltas, doesn't it? But that isn't a problem, because this is completely analogous to us putting more than one restriction on the capital N when we're doing the limits for sequences. So this, I can just say that, so if x minus 1 is less than the minimum of 1 and epsilon divided by 12, well, this implies that x minus 1 is smaller than both of them if it's smaller than the smallest, and we get this. And this expression here is our choice for delta, the minimum of these two conditions. And that's it. Now I've won. I've proven that I can get this as small as I want by making x minus 1 small, meaning I've proven that this limit holds when f of x is this expression